Section 8.5 is on annuities, methods of saving, and investments. This is part 1 of a 2-part video. It is a longer section. An annuity is defined as a sequence of equal payments made at equal time periods. And a great example of an annuity would be retirement accounts. So you're going to see a lot of mentions of individual retirement accounts, or IRAs, throughout this section. So whenever they ask you, how much money would you have in this retirement account if you deposit such and such money each month or each year, you're going to use the formula that I've written in the middle of your screen. So if P, instead of representing the principal, now represents the deposit made at the end of each compounding period. So this could be, again, a monthly deposit into like a retirement account, an annual deposit, but it's getting plugged into P in the formula. For an annuity that pays an annual interest rate, which is still abbreviated with a little r for rate again, and it's still compounded n times per year. The number of times the interest is recalculated is still little n. The value, in other words, the whole amount in the account, capital A, of the annuity after T years is the following. And as you can see, it is a longer formula. You should put a lot of parentheses in here, and if you have that graphing calculator, you can just type the parentheses right into the main screen. We have brackets, which are a type of parenthesis, so you can just use the normal parenthesis buttons there. We got inner parentheses in the numerator as well, and we have parentheses around the denominator. So we have 3 parentheses in this big old formula. Honestly, most of the battle here is just getting this correctly into the calculator, because you're just plugging into a formula. So looking at example 1, it says to round answers to the nearest dollar. At age 25, to save for retirement, you decide to deposit $200 at the end of each month into an IRA, in other words, an individual retirement account, that's our abbreviation for that pays 7.5% compounded monthly. So the interest is recalculated each month. Part A, how much will you have from the IRA when you retire at age 65? And then B, find the interest. So we're going to see with situations like this in real life that compound interest is a good thing when it's money in our pocket, like retirement accounts, savings accounts. As that interest accumulates, you're going to get interest on top of interest, and a lot of our deposits will grow with the interest as well. So we're really going to make out. Whereas in future sections, we're going to see that compound interest is not such a good thing when we're borrowing money, like with credit cards, because we end up paying a lot out for interest in that case, or for like car payments or a mortgage on a home. Okay, so whenever it mentions retirement accounts, how much money will you have in them, that's your cue to use our new formula. So the whole amount, A, equals. Looking at the formula, remember P, the principal in this case is the deposit made, and your deposit is $200. In fact, why don't I do this? Off to the side, I'm just going to write what we're plugging into what. So P equals 200. The rate, well, that's a percentage that you're being charged, or in this case, not being charged, that the percent that the interest is going to grow, since we're talking about like an investment scenario here. But the only percent number I see is 7.5%. Sure enough, that's the rate. You're going to always convert it to a decimal before you plug it into any formula, though. So that's 2 hops to the left. So 1, 2. Plug down your new decimal point. I know that's kind of messy, but 7.5% is the same as 0.075. 0.075. As just a pure decimal number, that interest rate. The other numbers I see a bunch of n's in the formula. N is the number of times it will be compounded. And if it says, like here, compounded monthly, n is equal to 12. So n is very similar to the last section. And the only other thing that we're missing in the formula here is I see some t's for time. It's still going to be in years. Remember, I draw a curvy t just so it doesn't look like a plus symbol. So in the context of these questions, that's the number of years the money is going to sit in the account. So let's think about this particular question. It says we start making deposits at age 25. And we stop making deposits and we take out the money in Part A at age 65 is when we retire. So from 25 to 65, we'll just simply subtract. If I take 65 minus the 25, that tells me I'm going to be making monthly deposits into my retirement account for 40 years. So T is 40 years going into time T. Got to really read these questions carefully. Okay, so now we know what to plug into all the variables, so plug it in. So we said the P was 100, that was the deposit, bracket parenthesis, 1 plus R over N. R was 0.075. over n monthly, n was 12. Raised to the n times t power in the formula. Well, again, n was 12 times the time t was 40. So both n and t are floating in the exponent spot. Don't forget, there's a minus 1 hanging off the end always. And go ahead and close those brackets. Bring down the main fraction bar. On the bottom, parentheses r over n. So parentheses r again was 0.075 over n again was 25. So step 1, you read the question carefully and plug correctly into all the variables of the formula. Now step 2, we're going to get prepared here to punch this whole big thing into the graphing calculator. Keep in mind that brackets are just a type of parenthesis. So I'm just going to use the parenthesis buttons when I see the brackets. In fact, if you don't want to write brackets, you could just rewrite them as parentheses. So like here in blue, I'm going to make this left bracket into a parenthesis. And I'm going to make this right bracket into a parenthesis as well. Just to remind myself to hit that normal parenthesis button in the graphing calculator. Just like with the previous section, I would encourage you to take care of the exponent multiplication first, then put the whole big long formula into the calculator. So when I look at the exponent, it says 12 times 40. That's going to give me 480. So I'm going to slash it out in blue and write 480. There we go. Now we're just going to take our time and punch the whole thing into the graphing calculator. And remember, we're going to round the answer, it said, to the nearest dollar. So there's not going to be any decimal point. It's going to be 0.0, in other words, after it's rounded and done. Okay, typing it into the calculator. We had 200 first. I'm just typing in the right side of the equal symbol there. So 200. And then we technically had a left bracket following that, but we said it's the same as a left parenthesis. The left parenthesis is above the 8 button. Then we have another left parenthesis. So you should have 2 left parentheses touching every time you use this formula, just like I have on my main screen here. 1 plus point, decimals on the bottom row in the middle, 0.075, divided by, for fraction bar, 12. Close the inner parentheses. The exponent button is this up arrow above the division key, so I hit the exponent button. There we go. Cursor is now up in the air like an exponent. 480, because we already multiplied the exponent out. Hit the right arrow key to bring that cursor back down before you keep typing. And then -1. Close your brackets, which is the same as a right parenthesis. Whew, so that was the numerator. Divided by for the main fraction bar. Parentheses around the denominator, so left parenthesis, 0.075 divided by 12, and close the final parentheses. Every time you throw down a left parenthesis, somewhere down the line you should have a right parenthesis so that everything is closed. If you wanted to check before you hit enter, you can use your left arrow key to scroll over and just make sure that everything looks exactly how you have it written on your paper. Again, we're using just normal parentheses every time we see a bracket. And once it looks good, hit enter for equals. Rounding to the nearest dollar, that's the digit right before the decimal point. So to figure out how to round it, I'm going to look at the digit after the decimal point. It's a 4, meaning round down, so keep the ones spot the same. So that's $604,764 in that retirement account after 40 years. Jotting that down, I'm going to write approximately $604,764 as my final answer. Now we need to find the interest. So that's everything that grew and accumulated on its own. So in other words, take the full value that's in the account at the end and subtract away all the deposits that you made to see the interest alone every time. So doing that in black, interest equals the full amount was $604,764. I'll put A for full amount to label it there, minus all the deposits you made into the account, because interest is not any pennies that you put in there. It was just how it grew on its own there. So let's think this out logically. All the deposits, all the money we put into the account. Well, we deposited $200, so 200 times, I'll use parentheses for times. We made this deposit at the end of each month, so times 12 months in a year. So that would be for 1 year, how many deposits we made, 200 times 12, but we did it for 40 years, so times 40. So take the deposit amount, which was 200, times the number of times in a year you make it, in this case 12 because it was monthly, times the 40 is the number of years we made those deposits. And you could do it all in the calculator longhand, or you could do it as one line in the calculator. If you want to do it step by step, order of operations, you would multiply first. So if I do the 200 times the 12 times the 40, I'm going to type it into my calculator as well here. $96,000 is how much we've deposited at the end of 40 years after making a monthly deposit on time every month for 40 years. So bring down the 604,764. Bring down the minus sign. I just multiplied this deposit stuff and got 96,000. So now as the last step, do your 604,764 minus the 96,000. I'm going to erase because I'm running out of room. After you subtract that, you should be getting 508,764 as the final answer. So equals 508,764 after you subtracted that last line. So just be really careful, especially come test time. you have to read the directions carefully of how far to round. Because if you don't follow the directions, and let's say like on part A, you rounded to the nearest cent instead of the nearest dollar, that answer would affect your answer to part B, so then part B would also be wrong. It'll trickle into the following parts of that same question. So just make sure you read how to round each answer very carefully, because it does go back and forth a little bit on the homework and on the test between wanting nearest cent versus nearest dollar. But yeah, wow, look at how much of that was interest. The bulk of your retirement account interest, $508,764 of your whole amount there came from just interest alone. Very, very nice. You didn't pay a cent of that interest. That's just what accumulated and grew on its own. Let's try one more of these. So it says, example 2, suppose that when you are 35, you decide to save for retirement by depositing $1,000 into an IRA at the end of each year now for 30 years. Round answers to the nearest dollar. If you can count on an interest rate of 10% per year compounded annually, A, how much will you have from the IRA after 30 years? And then B, find the interest. So very similar to the last example, but now it's compounded annually rather than monthly, and we're making annual deposits instead of monthly deposits. The first thing I'm going to do is rewrite the formula at the top of the screen, because they're talking about a total amount in an IRA. So the whole amount A equals P times 1 plus R over N. And actually there was a bracket here as well, because remember there were two left parentheses touching right after the P. Close those inner parentheses, raise to the N times T power. I'll make another curvy T there, minus 1. Close the brackets, all over, parentheses R over N. Now, when you click on view an example for a compounded annually example like this, it might make the formula look a little different, but it's actually the same formula, I promise. They might be a little bit nice to you, and they might say, well, compounded annually means all the n's in this formula equal 1. So they might have already went ahead and replaced all 3 n's in the formula with 1. But just as a heads up, it is actually the same exact formula. So keeping that in mind, I'm going to write off to the side what all we're going to plug in. So we said N was 1. P represents the deposit amount, which is 1,000. R, the interest rate, 10% converted to a decimal. Well, 10%, if I move the decimal point, which I can assume is at the end of the 10, 2 hops to the left to convert it to a pure decimal. It's 0.10, or you could write 0.1, same thing. I'll just write 0.10 as my R. Reading these questions very carefully. We still need the time in years that the money is going to sit in the account, and the time that we're going to be making deposits as well here. Technically, T is the time that the money is going to sit in the account. Well, we are going to, let's see, it starts when we're age 35. However, this question, they just tell you that you're going to be making deposits into this IRA, and then the money's going to sit there at the end of each year for 30 years. So T equals 30. You have the retirement account, and the money sitting in there for 30 years. So T equals 30. Okay, so now we're ready just to plug into the formula, and we'll type it into the calculator. So A equals, our deposit amount P was 1,000, bracket, parenthesis, 1 plus R over N. R was 0.10. Over N is 1, close the inner parentheses, raise to the N times T power, N again was 1, times the time was 30 years. And don't forget the minus 1 at the end of that formula. Close the bracket. All over on the bottom, parentheses, R was again 0.10 over N, compounded annually, so N was 1. The interest is recalculated once a year, in other words. If you wanted to simplify, you could, like 0.10 divided by 1 is just 0.10, and the view and example is going to do that. Or if you want to just put it all in just like that, that's fine too into the calculator. I would do the exponent real quick first though. It's a real easy one. 1 times the 30, for of course 30 again is the exponent. Here we go. Typing it in, we had 1,000. We said use the left parenthesis as a bracket, so parenthesis, parenthesis, 2 left parentheses touching always in this formula. 1 plus 0.10 divided by 1. Close the inner parentheses. Don't forget the exponent button. It was raised to the 30th power. Don't forget to hit the right arrow key to bring your cursor back down to ground level. Before you hit minus 1, close the bracket, which you can just use the normal right parenthesis above the 9 key. Divided by, for fraction bar, parenthesis, 0.10 divided by 1. It's not so bad once you get the hang of it. Close the parentheses. You might want to use your left and right arrow keys just to skim everything you've typed in, just to make sure it looks like what you have written on your paper. Once you're ready to go, hit enter. It said round to the nearest dollar. Because the digit after the decimal point is a 0, I'm going to round down, meaning keep this 4 here the same. So that's approximately $164,494. Jotting that down, so approximately $164,494 rounded to the nearest dollar. Part B, find the interest. So how much of that $164,494 is just interest alone as opposed to the deposits you made? So interest, I'll write it in blue. For these questions, you're going to take the whole amount, the final amount, and you're going to subtract the total number you deposited. I'll just write minus total deposits. Just like part B of the last slide in this video. So the whole amount was $164,494 minus, let's think about the total deposits we made logically. We made a $1,000 deposit, so 1,000 times, we made it once a year, so it's technically just times 1, whereas in the last example we had to times it by 12 because it was a monthly deposit. And we do this annual deposit for 30 total years, so times 30. You could do the whole thing like that, type it into the calculator just like that, or if you wanted to break it up, you would do the multiplication next. So 100 times 1 times 30 is, of course, 30,000. Bring down the 164,494. We haven't touched it yet. Now, take the 164,494 and subtract the 30,000 that you deposited, and we see that $134,494, so the vast majority of what you have in that retirement account at the end is just interest alone that accrued into the account. You would not type in the commas or the dollar signs, by the way. Just the values typically into the My Math Lab homework. But if you're not sure, just read those directions carefully in the homework and it'll specify how to format those answers. What if these retirement questions, these annuity questions, were phrased a little bit differently? So what if you already know how much you want to have, so you're planning for the future, you already know your final amount A, but you're asking yourself, how much should you deposit now? I have that phrase in quotes off to the side. So when you see something like, how much should you deposit each month, and you're planning for the future, you're actually using the same exact formula. I know it looks a little different, but all they did was they rearranged this formula and they solved it for P, which represents the deposit amount. So looking at example 3, it says, suppose that once you complete your college education and begin working, you would like to save $20,000. So that's the whole amount you want over 5 years to use as a down payment on a house. You anticipate making regular end-of-month deposits in an annuity, because retirement plans was just one example of many of a type of annuity, so this is a different type of annuity, that pays 6% compounded monthly. Part A, how much should you deposit each month? Round up to the nearest dollar. Whenever we're using a formula where we're planning for the future, we should always round up. Don't use normal rounding rules. Always round up to make sure that we're not even a few cents short of meeting our goal. If we want $20,000, we don't want to even be a cent short of that. So by rounding up, ensures that we definitely meet that goal. We might even be a few cents over, but that's okay. And notice the difference in phrasing. So it's an annuity, but instead of asking you what's the whole amount you would have after so and such deposits are made over such time, it says, how much should you deposit? So that tells you, okay, you're planning for the future, you're solving for P for a change. So P equals the whole amount A that you want when this is all said and done is $20,000. And if it helps, feel free to write off to the side what you're plugging into everything. So A is $20,000. The interest rate is 6%. When you convert that to just a pure decimal, 2 hops to the left, it's the same as 0.06. The N, well, if it's compounded monthly, N is 12. The interest is recalculated 12 times a year. And then the time in years is 5 years, according to the original question. So T equals 5. So it's really just a matter of plugging into the correct formula. So we just did A, and we said times R over N. So times R was 0.06 over N is 12. Divided by, if you don't like the brackets, you're just going to use the parenthesis button anyway. So feel free to make these brackets into parentheses if you prefer. So parenthesis, another left parenthesis, 1 plus R over N, so that's 0.06, for N was 12. Close the inner parentheses, raise it to the N times T power. So N was 12 times the time was 5. Minus 1, and close the bracket. I should do that in blue, just to show that that was originally a bracket. Whew. Let's now do the exponent first before we put the whole thing into the calculator. So I'm going to do the 12 times the 5, and that gives me 60 as the exponent. Now let's punch it all in. Remember, we're always rounding up, and this says to the nearest dollar. So we had 20,000, parenthesis, 0.06 divided by 12. Close the top parentheses, divided by for fraction bar. 2 left parentheses, because the first was the left bracket, then the left parenthesis after that. 1 plus 0.06 divided by 12. Close the inner parentheses. Exponent button. We got 60 after we multiplied out the exponent. Right arrow key to bring that cursor back down to ground level before you type in the -1. Close your bracket, which you can just use the right parenthesis above the 9 key. If you want to use the left and right arrow keys, just to make sure everything looks like you have it on your paper, that's fine. But once it looks good to go, you're going to hit enter. And it says round up to the nearest dollar. So we're always rounding up regardless, not using normal rounding rules. I look at the dollar spot right away for a change, and that 6 is going to automatically round up to a 7. So that's $287 deposit you would have to make each month. Let's go ahead and jot that down. So we said you would need to make approximately a deposit of $287 each month to ensure you get at least the desired amount of $20,000 in 5 years based on this particular type of annuity's interest rate. Looking at Part B, it says how much of the down payment comes from deposits and how much comes from interest. So the overall down payment was $20,000. So of that $20,000 we're going to have in the account after 5 years, what portion of it, in other words, is made from deposits and what portion is made from interest. Let's start with the deposits part, because this is actually 2 questions in one. And we can just think it out logically. We don't need a formula here. So the total deposits equals, well, we're making a deposit, we said in Part A, of $287. Times, we're making them each month. So that's times 12, since of course 12 months in a year. So that tells us how much we've deposited in 1 year. But we're going to do this for 5 years, so times 5. So we're going to do 287 times 12 times 5 on the calculator. And you should be getting $17,220 of the total $20,000, in other words, is going to come from our deposit money. Now, what portion is interest? Well, let's just simply subtract. So the interest equals, just like on the previous examples, you take the whole amount, which is the $20,000 that you have in the account, minus the total deposits we made. Well, we just said in black here, that's $17,220. So 20,000 minus 17,220 means that 2,000 rather, big difference, $2,780 of the 20,000 was from interest alone. Now keep in mind that's actually really good. I know it's not as much interest as the previous 2 examples, but we're only let the money sit in the account for 5 years. So just picture if we let that money that we're depositing sit in the account and just keep compounding for more years. Then the interest is just going to keep getting better and better over time for a savings or investment scenario like this anyway. You may see some vocabulary in the homework and even on the test, so it's important we're familiar with the difference between some of the main types of retirement accounts, the main types of IRAs. So the first type of retirement account is a traditional individual retirement account, or a traditional IRA. And for this traditional IRA, you do not pay taxes on money you deposit. You can start withdrawing money from this account when you are 59.5 years old. The withdrawals are going to be taxed, however. And please keep in mind, for all these accounts I have on the bottom of the screen, there are going to be penalties if you withdraw money from your account before age 59.5. Looking at the second type of IRA, the Roth IRA, it's kind of the opposite of the traditional in that you do pay taxes on money you deposit, but you can withdraw your earnings tax-free when you're 59.5 years old. Although your contributions are not tax deductible, your earnings are never taxed, even after withdrawal. And then there are a whole bunch of employer-sponsored retirement plans. This would include like your 401ks and your 403bs. And these plans are set up by the employer, obviously, who often but not always, makes some contribution to the plan on your behalf. This is unfortunately not offered by all employers. So, for example, if maybe, depending on who your employer is, they might say, okay, well, we'll deposit $100 every month into this retirement plan until you retire, but we're going to match your contribution. So if we put in $100 every month, you're going to put in $100 every month. But there are various, of course, employer-sponsored retirement plans. So it's just important that you're familiar with what retirement plan options you have for where you work at.